Hello everyone. In today's lesson, we're going to be covering the addition rule of probability. So the addition rule states that we should let A and B be events on our sample space. And there are two cases for the probability of our union. So let's say that we have A or B. Now, if you watched my video on set theory, you would know that this is called the union, which we also refer to as an or statement. And it just means you take anything that's in A, or anything that's in B, or anything that's in both. So if we were to draw this as a Venn diagram, it would look something like this. You've got your outcomes in A, you've got your outcomes in B, and it is anything in A, and it's anything that's in B, and anything that they share between them. So when we're looking at the probability of A or B, what we're going to do is we're going to take the probability that I get something that's in A. Plus, we also want the probability of getting something in B. But now you might notice when I shaded this in, we double counted this middle area. So what we actually need to do is we need to subtract out the probability of A and B. And this is the addition rule of probability. If you have the probability of some event A and some event B in the sample space S, then the way you find it is the probability of A plus the probability of B minus the probability of any overlap that the two events have. This specifically is when you have events that are not mutually exclusive. Which, if you remember, mutually exclusive just means that if one event occurs, the other could not have occurred. So an example of mutually exclusive events drawn in a Venn diagram would be something like this. You've got A over here, you have B over here. So if I have something that's in A, it cannot be in B because they are mutually exclusive. They have no overlap. If they're A and B are mutually exclusive, then this term, so we have A and B. Well, there's nothing that A and B both share. So this would be the empty set, meaning that the probability of A and B is equal to 0. So when you have mutually exclusive A and B, it means that your formula should be the probability of A or B is just equal to the probability of A plus the probability of B. Because this term falls apart. Because this term goes to 0. Which really, it is still the same formula. It's just that instead of having the minus probability of A and B, we just don't include it if they're mutually exclusive because this just goes to 0. Now, one thing I actually wanted to talk about before we move on to doing some examples with this is that this is actually a special case of this. And this is actually the special case of a much broader defined mathematical concept. This is called the Inclusion-Exclusion Principle. Now, this isn't something you're going to be tested on in the class, but I thought it would be interesting to kind of show you how this works. So we looked at the simplest case when we had probability of A or B. But what about if we wanted to know about the probability of A or B or C? So again, I'm going to start by drawing a Venn diagram. So in this Venn diagram, we have A right here. We have B right here. And we have C right here. So what we're doing is we are taking the probability of A, which would be everything in A is counted, plus the probability of B, so everything in B is counted, plus the probability of C, where everything in C is counted. Now again, you might have noticed that we overcounted this middle part because we counted all of this 3 times, or some of it 3 times, right? This part got counted 2 times, this part got counted 2 times, this part got counted 2 times, and the last one, actually, the middle, got counted 3 times. So what we're going to do then is we're going to subtract out the probability of A and B, just like before. So we're subtracting out this part minus the probability of A and C. So we're subtracting out this part minus the probability of B and C. So we're subtracting out this part. But now what happened is we've subtracted out all of the intersections of A and B, A and C, and B and C, but we actually subtracted out the middle too many times. So we have to add that back in, plus probability of A and B and C, the thing that they all share. And then you could continue doing this beyond this. So I'll give you one more example, and I'm not going to draw the Venn diagram for this, but if I have the probability of A or B or C or D, this would be equal to the probability of A plus the probability of B plus the probability of C plus the probability of D. So you do the probability of each single term. Then you subtract the probability of all of the doubles. So A and B minus probability of A and C minus probability of A and D minus the probability of B and C minus the probability of B and D minus the probability of C and D. And again, we've taken too many out, so now we have to add in the triples. So this would be plus probability of A and B and C plus the probability of A and B and D plus the probability of A and C and D plus the probability of B and C and D. I think I have all of them. And then the last thing is, we added too much back in, so now we have to subtract out the intersection of all of them. Probability of A and B and C and D. And then you could continue doing this on for every extra set that you've added in. So you include the singles. You subtract out the intersection of 2. You add in the intersection of 3. You subtract out the intersection of 4. You add in the intersection of 5. So basically every odd number of intersections, so 1, 3, 5, 7, so on and so forth, you would add those terms in. Every even intersection, so A and B, so 2, 4, 6, 8, so on and so forth, you would subtract those. And this would work for any number of sets. So let's look at a couple examples. A single 6-sided die is rolled. What is the probability of rolling a 2 or a 5? So for a single 6-sided die, what is the probability of getting a 2 or a 5? Well, in this case, these are mutually exclusive, right? If I roll a single die, I cannot have an outcome that is both a 2 and a 5 at the same time. So in this case, it would just be the probability of getting a 2 plus the probability of getting a 5, which probability of getting a 2 is the number of ways that I can get a 2, or the number of successes, which means 1, right? If I roll a 6-sided die, there's only one face that has a 2 on it, out of a total of 6 faces. Plus, probably getting a 5. Again, there's only one 5 out of the total 6 possible rolls. So we get 2 over 6, which is 1/3, or about 0.33 for our probability. Second example. In a stats class of 75 students, 45 are boys and 30 are girls. On a test, 14 boys and 10 girls made a grade of A. If a student is chosen at random from the class, what is the probability of choosing a boy or a student who received an A? Now in this example, they are not mutually exclusive because you have the category boys, you have the category received an A, and there's an intersection, boys who received an A. So we want the probability of selecting a boy or a student who received an A. So in this case, we first need to set it up. So this is going to be the probability of selecting a boy plus the probability of selecting a student who got an A minus the probability of selecting a boy that also got an A. So looking back at the problem, we have a total of 75 students where 45 of them are boys. So that means the probability of selecting a boy is 45 out of those 75 total students. On the exam, 14 boys and 10 girls made an A, meaning a total of 24 students made an A out of the total 75. And now we need to subtract out the number of boys who also got an A. So that means 14 out of 75. So doing this will get us a probability of 0.733. Now let's do another example where we're going to pull out a card from a deck of cards. If we draw one card out of a deck of cards, what is the probability that it would be an ace or a king? So for a deck of cards, what's the probability we get an ace or a king? So before you do this, first thing is think about, is this mutually exclusive or not? And in this case, it is. Because if I draw a card and it's a king, that means that it could not also be an ace, right? Being a king precludes the fact that it is an ace. So this would just be the probability of drawing an ace plus the probability of drawing a king. Well, in my deck of cards, there are 4 aces. There's an ace of hearts, diamonds, spades, and clubs out of 52. Plus, kings, same thing. There's a king of hearts, diamonds, spades, and clubs. Which then gives us, and if you wanted to, you can include the intersection, so minus 0, because there's no interaction between them, which then gives us a probability of 0.154. In this example, we want to see that if we roll 2 dice, we want to find the probability that the sum of the dice, so the outcome of the 2 dice, is an 8 or a 9. So we want to get the probability of getting an 8 or a 9. Now think about this for a second. Are these mutually exclusive? Well, the answer is, in this case, is yes, because if I roll the dice and I tell you that I got an 8, then you know for a fact that I could not have gotten a 9 because you either got an 8 or you got a 9 for the outcomes of your dice. So then for this one, we want to find the probability of getting an 8 plus the probability of getting a 9. Now, you might wonder, how do I figure out very quickly what the probability of getting an 8 is? And I can tell you off the top of my head, this is 5 over 36, this is 4 over 36. And you might wonder, how do I know this? Well, let's actually write down all of the possibilities for when we roll our dice. So we have S is equal to, curly bracket, and now I have to put the actual outcomes of the dice. So we're going to do it in terms of die 1 and die 2. So this is going to get, I can get a 1, 1, which is equal to a 2. I could get a 1, 2, which is equal to 3. I could get a 1, 3, which is equal to 4. I could get a 1, 4, which is equal to 5. I can get a 1, 5, which is equal to 6. And I can get a 1, 6, which is equal to 7. Or, I'm going to do the same thing for my 2s. 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, and 2, 6. I'm going to do the same thing for my 3s. 3, 1, 3, 2, 3, 3, 3, 4, 3, 5, 3, 6, 4, 1, 4, 2, 4, 3, 4, 4, 4, 5, 4, 6, 5, 1, 5, 2, 5, 3, 5, 4, 5, 5, 5, 6, and almost done. 6, 1, 6, 2, 6, 3, 6, 4, 6, 5, and finally 6, 6. And then we end our set with another curly bracket. Okay, so now you can see all the possibilities that we have. Well, if you actually look at the diagonals, you'll see that this 1 and 1 is the same thing as giving us a 2. 2 and 1 and 1 and 2 are both ways that I could get a 3. 3, 1 is 4, 2, 2 is 4, 1, 3 is 4. So there's 3 ways that I can get a 4. There's 4 ways that I can get a 5. There's 5 ways that I can get a 6. And there's 6 ways that I can get a 7. And then it starts going down. There's 5 ways that I can get an 8. There's 4 ways that I can get a 9. There's 3 ways that I can get a 10. There's 2 ways that I can get an 11. And there's 1 way that I can get a 12. And this is actually how I knew off the top of my head that for a probability of 8, there were a total of 5 ways that I could get an 8 and a total of 4 ways that I could get a 9. And it's because it follows this pattern. In fact, if we were to draw a little graph to represent this, if 7 were at the middle, this would have 6 outcomes. And then going out from there to 6 or 9, there would be 5 outcomes. Going out from there to 5 and 10, there would be 4 outcomes. Going out from there to 4 and 11, there would be 3 outcomes. For 3 and, I forgot my 8, this should be 8, 9, 10. So 3 and 11, there should be 2 outcomes. And then finally, for 2 and 12, there will be 1 outcome. So really, if you're ever doing 2 dice roll problems, so 2 6-sided dice, the easiest way to know any number of outcomes is start in the middle at 7. It's the most common outcome with 6 total ways you can get a 7, which is you can get a 1 and a 6, you can get a 2 and a 5, you can get a 3 and a 4, you can get a 4 and a 3, you can get a 5 and a 2, or you can get a 6 and a 1. So with those 6 ways that you could get a 7 being the most common, you then from every value you go out from 7, so 6 and 9, you subtract that by 1. So there's 5. You go out another one, which would be 5 or 6 and 8. 5 and 9, then you go down another value, which is 4. You go down to the next values, 4 and 10, you get down to 3, and so on and so forth. And you can actually use that pattern to very quickly figure out how many there are. So for this example then, for our probability of 8, we said that there were 5 out of 36 ways that I could get an 8. And for 9, there were 4 out of 36, meaning that we have a total of 9 out of 36, which then gives us, if you were to simplify this, 1/4, or a probability of 0.25. And that's all there is to doing our addition rule of probability. You start with the probability of A or B, and it is the probability of A plus the probability of B minus the probability of the intersection of A and B. If A and B are mutually exclusive, the intersection is the empty set, so the probability of the empty set is equal to 0, meaning that term goes away, and you can just use probability of A plus the probability of B. Thank you for watching. To continue learning, click the linked video here for the next lesson. If there's a topic you'd like me to cover, let me know in the comments. Don't forget to subscribe, and I'll see you in the next video.